In Lecture 3, we introduced the concept of resonance, and I showed you how to draw resonance structures and how to delocalize electrons. Now what we're going to do is to see if we can recognize patterns in drawing resonance structures. So just before we get started, I want to define what a vinyl position is and what an allylic position is. So here, highlighted, we have a double bond. The carbons directly attached to the double bond are vinyl carbons. Now the carbons that are next to or adjacent to the double bond are called allylic carbons. And when we say next to or adjacent, we mean that they're separated by exactly one single bond. So there are 5 patterns that we're going to learn to recognize. We can have a lone pair next to a double bond. We can have a lone pair next to a positive charge. We can have a pi bond next to a positive charge. A pi bond between 2 atoms, where one of the atoms is electronegative, or pi bonds going all the way around the ring. So let's start with a lone pair next to a pi bond. So when we say next to, we're talking about that allylic lone pair. So that means that the lone pair is separated from the double bond by only one single bond. No more, no less. So let's look at the molecules below here and see where we might have an allylic lone pair. So first let's start with drawing all the lone pairs in. So when I draw the lone pairs on this oxygen here, and let's just name this functional group so we get used to doing that. We have an amide. Okay? We can see that the lone pairs are on the oxygen, and then there's the double bond. So this is not an allylic lone pair. Okay. So here, if we come to the oxygen again and draw the lone pairs in, okay. Here we have a carbon-carbon double bond. Here's our single bond. Now, if the lone pairs were on the carbon, they would be allylic. But because they are on the oxygen, they are not. And just to add to this, this is a ketone. Now we come here, we draw the lone pair on the nitrogen. Again, the double bond is right there, attached to that nitrogen, not allylic. Here we have our carbon-carbon double bond, one single bond, and then a lone pair. So this is an allylic lone pair. Here we come back to the amide, and in the first structure I did not draw in the lone pair on the nitrogen. And again though, if we now look at that nitrogen, here the lone pair is adjacent to this pi bond. so that this is an allylic lone pair because there's one single bond. If I draw my lone pairs in on the oxygen, here's a carbon-carbon double bond, here's a single bond, and here's a lone pair. So this is allylic. This here will also be allylic. And finally, when we come to this we've already done this one, and this was not allylic. So you can see you need to have a lone pair next to a pi bond, and it can be a pi bond with a heteroatom. So here, if we practice the pattern, we have the lone pair next to the pi bond. And so first I'm going to draw the curved arrow in. Okay, when I draw that curved arrow, I have to push another pair of electrons. So our starting structure has a negative charge, and our final structure has a negative charge. Here we start with a neutral structure. If I draw the lone pairs in, first I push the electrons between the oxygen and the carbon, and then I will push the electrons out to the carbon. So now one of the lone pairs is making a pi bond, so we get a plus charge on the oxygen, and we made a new lone pair on the carbon, and so we have a negative charge. So you can see while our original structure was neutral, our final structure, even though we did make charges, is also neutral. The next pattern to recognize is when we have a lone pair next to a positive charge. Again, we define next to as that lone pair being separated from the positive charge by a single bond, no more, no less. So let's see if we can identify the compounds which demonstrate this pattern of resonance. So if we come to the first structure, we can see that we have a positive charge, one single bond, and then a pi bond. So this demonstrates the second pattern of resonance. Here we have no pi bonds. Okay. Oh, sorry. Let's go back. So this first structure does not exhibit that pattern of resonance because there are no lone pairs. The second structure does have the lone pairs next to the positive charge. So we have a lone pair, a single bond, and then the positive charge on that carbon. Okay. The second structure here does not have a lone pair next to a pi bond. next to a positive charge. Sorry, still stuck on the first pattern. This fourth one here has a lone pair, single bond, positive charge. And finally, our last structure also has our lone pair, single bond, positive charge. So if we were to draw the resonance structures as we did for the first pattern, I'll put my lone pair in for the nitrogen. I can push my arrow between the carbon and the nitrogen. So we had a positive charge in the first structure, and we end up with a positive charge now on the nitrogen. In this bottom structure here, for the nitrogen to have a negative charge, it must have two lone pairs on it and two bonds. If we push a lone pair, what we will see is that now our structure is overall neutral. The first structure is neutral, and our final structure is neutral, but there are no more formal charges. The third pattern is a pi bond next to a positive charge. Okay. So this is an allylic positive charge. This is where I was identifying resonance above when I wasn't supposed to. So again, next to refers to a positive charge that is separated from a pi bond by exactly one single bond, no more, no less. So if we look at these structures here, let's see if we can identify this pattern of resonance. So here we have a positive charge, single bond, pi bond. No pi bonds. In the second structure, pi bond, single bond, positive charge for the third, pi bond, single bond, positive charge for the fourth, no pi bonds. In the fifth, positive charge, single bond, pi bond. In the sixth, and then there are no pi bonds in that final structure. So we can think of a positive charge as a hole. It's a place that electrons are missing. So what we're going to do is we are going to push the electrons to plug the hole. And then this creates a new hole nearby. So a new hole would be a new positive charge. We need to remember when I draw the arrows that the tail of the arrow is going to be placed on the pi bond, not the positive charge. We are not going to ever push the positive charge. So here, the pi bond is what moves. And that generates a new hole. If we go to the next example, first I move the pi bond as indicated. And I make a new positive charge. Then I can push again. and end up with this third structure here. So again, it's the pi electrons that move. The fourth pattern of resonance is when we have a pi bond between two atoms where one of those atoms is electronegative. So we're going to always move the pi bond onto the electronegative atom to become a lone pair. So if we look at this first example, we have a pi bond between two carbons. The two carbons are equal electronegativity, so this does not satisfy that pattern of resonance. Here we have a pi bond between a carbon and an oxygen. So we can move that pi bond onto the oxygen. So this does satisfy that. Like here we have a ketone, so this also satisfies that pattern of resonance. Here the pi bond is between the two carbons, so it does not. On the fifth structure, again, the pi bond is between the two carbons, so it does not satisfy that pattern of resonance. In the sixth structure, we have the pi bond between the carbon and the nitrogen, so that it does. And finally, again, we have a carbon-oxygen pi bond, so this also satisfies the pattern. So if we were to practice drawing resonance structures for this pattern, what we would do is we would push those pi electrons onto the oxygen. We create a negative charge on that oxygen and a positive charge on the carbon. If I do this one more time, you can see we can push the electrons onto the oxygen from the pi bond. And the oxygen gets a negative charge and the carbon a positive charge. Make my arrow a little bit neater there. The last pattern that we're going to discuss is moving pi bonds around a ring. And this we see in an aromatic system. So what you can see the arrows here, and we can move the pi bonds, and we have a new structure. So now I have several examples here. So I have molecule, let's start here. And the question says, which of the following is a correct resonance structure of A? So if I were to redraw this molecule in with the lone pairs, okay. So here we have a pi bond. These are allylic lone pairs. We also have a pi bond between a carbon and an oxygen. The oxygen is electronegative. So we can also push the pi electrons. So let's start with pushing the pi electrons onto the oxygen. That will generate structure 1. We could also then push the allylic lone pair but this structure is not an option or not a choice. We come down to the next structure with the nitrogen. And what we can see, if I draw the lone pair in on the nitrogen, here we have a double bond, single bond, and then lone pair on the nitrogen. So what we can do is we can push that lone pair in and then push the pi electrons. This would generate a positive charge on the nitrogen and a negative charge on the carbon. And we can see that in structure 2. So this would be pattern number 1 with the allylic lone pair. Finally, we come to the chlorobenzene, and what we can do here is we can automatically eliminate structure 1 because there are 5 bonds to carbon. Structure 2 is missing pi electrons. Structure 4 has a fluorine. If we look here to see structure 3, those electrons moved out onto the carbon. This would come in the form of the pi electrons moving around the ring, but it would not be a major contributor to the resonance structure. So this ends our discussion of recognizing patterns in resonance.